Professor Marilyn. She is going to be giving us a talk about engineering and processing of nanocomposites. Again, we started with nanocomposites. We continued with components for nanocomposites and dispersion of nanomaterials. And now we're going to speak about how really combine them to have effective nanopolymeric films, nanopolymeric fibers. And Professor Minos, the floor is yours, and thank you.
Thank you. Thanks again for the invitation. I'm going to talk a bit about the composite work that we've been doing in our lab, and it's focused on using nanomaterials for different fibers and films. I'd like to start with the acknowledgments. Lots of students have done this work coming through the lab and now in different careers. We've had our funding from NSF, DARPA, the Air Force, the Army. A lot of our work is mainly focused on fibers that are really for lightweighting and high modulus, high tensile strength. These are the faces. It's always nice to have faces with names of the students that have come through the lab over the years. So in our lab, we kind of focus on a few different things. We look at nanomaterials, but we look at conventional polymers because we're trying to use the cheapest materials. Obviously, nanomaterials are not very cheap, but we're trying to figure out ways to utilize them to get them into the market. And there's been a lot of work over multiple decades now. We haven't made a huge amount of success, but I think there's a lot there, and we're still kind of getting there. We look at the fundamentals in the lab. We do a lot of characterization, so we're almost fully experimental, but we do quite a bit of computational work, lots of mentorship and collaboration to make this all happen. So overall, just to give you a general overview of what we do in the lab, I have way more slides than I'll probably present, so I want to make sure you have a sense. We work with a variety of polymers, a lot of different nanomaterials. We focus a lot on carbon nanotubes. We also look at boron. We also look at hexagonal platelets and other types of things beyond tubes. And we study different form factors. I'm going to talk mostly about fibers and films here today. We look at a wide variety of loading, so from the very small amount of nanomaterial to a higher amount of nanomaterial. And the properties that we try to target are, again, competing with the carbon fibers, Kevlars, your high-performance materials. We focus a lot on interphase control, and so we are not chemists in the lab. We are polymer processing people, but we try to control the interphase region in these films and fibers because it has a lot of effect on the overall properties, which I'll show you today. So I have a few different areas that I hope to touch on. Again, my slides are going to have way more information than I'm going to talk about, but it's just there because I know we'll have some time for discussion in case anyone wants to go into detail. So I'll first start with dispersion because that's the biggest issue that we have when we utilize nanomaterials. And I know there's been a few talks that have looked at this already, but we'll talk about it in the context of what we're doing in my lab. So this would be a cross-section of a composite material containing about 50 by weight nanotubes in a polymer. So this polymer is polyacrylonitrile, which is a precursor for carbon materials, single-wall nanotubes. And if you look at this cross-section, we've done a pretty good job by all standards of making sure we've dispersed these nanomaterials. So you can see it's very uniform across this, the cross-section, even though we have a large amount of nanotubes. However, when we incorporate a phase separation process where we treat the nanotubes with a non-solvent and solvent system, what happens is in that same film we see a two-layer structure. We see something where all of the nanotubes look to have fallen out of the film. However, when we look closely at this material, we can see that within these two layers we have two different sets of nanotubes, essentially because the nanotube sample is heterogeneous. You have bigger and smaller bundles depending on how you mechanically disperse these materials. The polymer is able to capture some of it, and some of it is actually rejected by the polymer. So we've been looking at this as a means of trying to capture the polymer or the nanomaterial we want to use in a particular polymer matrix as a better way of dispersing these materials as opposed to just adding more and more loading into the system. So we studied this in detail and we looked at a lot of different temperatures, non-solvent, solvent mixtures, a lot of different conditions to try to understand it. And you can see at the very top, this looks like a composite that I showed first where everything looks fairly uniform. And as we go down, you can see there we have this very nice clean bilayer, and that depends on the solvent-non-solvent ratio as well as the temperature that we use when we introduce the polymer. So by understanding this, we've been doing this with different polymers, different molecular weight polymers, and different nanomaterials. We've been finding these essential relationships where a particular polymer, particular nanomaterial can give us these different types of arrangements, and we can use that as a means of learning how to disperse them better for the ultimate composite. And I will say the polymers that we're using in these cases are long chain polymers, usually linear polymers, because we spin fibers. So we need that type of polymer for a fiber. So what we find is that in these different layers, and when we do a good dispersion, this is a typical nanotube-rich layer where the nanotubes have essentially been rejected by the polymer. And this is one where it's been captured by the polymer, and you can see very quickly the difference in the bundle size and uniformity of what's captured by the polymer versus what's rejected. So essentially you're using the polymer as a way to pull out the more uniform bundles and reject what is agglomerated and so forth, which is a great thing because it gets rid of those defects in your ultimate composite. And we've done some analysis on this for different nanotubes, different polymer systems, and what you can see very clearly is that in that nanotube-rich layer, again, you have a very heterogeneous mixture of size of bundles, but inside that polymer layer, every time you get a much more uniform distribution of the nanomaterial. And we've studied this for a bunch of different polymer molecular weights, and we can actually see a very nice correlation between that. And we've published a bit of work on it to show that basically it's related to the free volume in the polymer. As the polymer forms a coil or a solvated coil in a different solvent system, it has a certain amount of free volume, and it can actually capture or wrap itself around the nanomaterial. So if we do that in a very controlled way, we essentially can pull out the nanotube bundles that are more easy to interact with for that particular polymer. People have shown this with DNA, for example. We're essentially doing this with different polymer, long chain polymers. We've studied this computationally as well. So again, my lab is primarily experimental, but in the computational sense, we wanted to understand this because when you're working with nanotubes, everything is black. You can't see anything, and the microscopes don't always get everything. So by changing the solvent-non-solvent interaction, we can change the way the polymer in the green here is interacting with the various bundles. And we can create phase diagrams that actually help us to tune our processing, where in some cases, different windows of nanotubes, solvent and non-solvent, as well as the polymer, allow us to have a better interaction between the polymer and the nanotube bundle, or less better interaction. And what we find is that if I'm working with one particular polymer, so a polymer that's more, for the polymer itself, a solvent, that's more for the polymer, that's great for the polymer, not so great for the nanotubes. If I work with a non-solvent, then the two of them are running away from each other because they hate the system. So finding the right balance between the solvent-non-solvent mixture is actually the sweet spot. And so these phase diagrams have given us insight. So that's a bit about how we're using this dispersion. So I'll move now to how we're using that to put into the composite. So when we first started with trying to understand the polymer, these long chain polymers with these nanomaterials, we essentially knew that if I have a polymer solvent mixture, I had a better chance of dispersing the polymer, dispersing the nanomaterial, in that system. And people have mentioned that today. You're adding more polymer layer around the nanomaterial, so you have more steric interaction. They're going to stay apart. And we found that if we disperse these by sonication and add some heat treatment, we could create various coatings around the nanomaterial, but this is not using any phase separation method, so you're just kind of getting what you're getting. And this was nice because we could learn about sonication, we could learn about using different heat treatments, post-processing, even using some shearing, and we could cool it, undercool it, control crystallization. We could look at when we got very nice tubular coatings versus shish kebab coatings versus nothing that's very special. We could do X-ray characterization to understand it. So ultimately, we were getting a good sense of, okay, the polymer, when it gets around the nanomaterial, can form a particular structure, and we can control that to some extent. But now with the phase separation, we wanted to go a little further. So we studied this in a lot of detail. We studied crystallization of the polymer. We studied annealing. And in all these cases, again, we keep getting nice structures of polymer around these nanomaterials. So how could we then couple that to what we're doing in the phase separation? Well, with this system now, when we do our dispersion and we use phase separation, we're collecting essentially a paste, a polymer that is very well uniform and interacting with a certain subset of nanotubes, and we can remove all of the nanotubes or that nanotube-rich layer that we don't want, and we can create films or non-woven structures from that and study them. These are some examples of those structures that we've created, and when you're drying these, when you're processing them, they can be a lot of issues, so we've spent a lot of time really doing a good job of processing these, because we want to characterize them to understand this structure, to understand what this is doing mechanically. One thing that's very interesting about it is this is the polymer, this is the storage modulus, so you can see it changing as a function of the glass transition. It's going to drop off. But when you add these nanomaterials in the way that we've been adding it, the polymer doesn't behave any differently. So here, this is dynamic mechanical analysis. You can see the black line represents the pure nanotubes, but all of the composites that we've treated, essentially you can't see the polymer. It's almost like there is no polymer there. And that's because the polymer is not behaving differently from the nanomaterial, because when they're blended like this, they're perfectly interacting with one another. We can also see this again in the tangent delta curve. You can see the very red is the pure polymer, so it's got this nice tangent delta. Polymer is in all its other films, but I cannot see it. And what we've seen here is that we can change the mechanical properties. We're trying to understand it in these films, but when we heat treat these samples with annealing, these X-ray peaks here provide the evidence that the polymer is there. With annealing, we can't crystallize the polymer, but it's interacting so well with the nanomaterials because of this blended phase that it basically forms this perfect composite. So this is very exciting for us, and we want to be able to translate this into fibers because we want to make these really nice fibers. So early on, before we understood phase separation or been using that, the first set of fibers that we were making utilized that data that I just showed you about controlling the interphase using crystallization of the polymer around the nanomaterial. So for a polyvinyl alcohol system, we were able to use a setup in our lab where essentially it's a dry jet wet spinning, but we utilize some flow in order to create some elongation of the fibers as they're being spun. And what we did was we incorporated crystallization of the polymer at the interphase in some fibers, and in other fibers we just dispersed our nanomaterials in there. And at 5 weight percent, what we were able to see is that this first fiber just has a regular dispersion method. The second fiber incorporates some amount of this crystallization, and we can see that coating of polymer on our nanomaterials. And this is just one picture, but we saw this throughout. And you can see from the mechanical behavior that the control fibers are just the polymer fibers. When you disperse the nanomaterials in, you're getting a jump in properties, which you should expect, and this is what a lot of papers have done. But by controlling the interphase, I get a huge bang for my buck. And these were fibers that we made with upwards of 5 gigapascals tensile strength. So better than most of the high performance materials out there. And it is repeatable. And so this is something that really showed us that it's not about how much nanomaterial you put in, it's about making sure that the nanomaterials interact very well with your polymer matrix and how to control that. So one of the things that we've been doing is harvesting this nanomaterial paste. So this is what it looks like when we do the phase separation and we capture that phase of polymer that's very much interacting. It looks like this nice blob, and we're now incorporating this into our dopes in order to spin fibers. This is very challenging because we use a non-solvent in order to create this. So you have to then remove all of that non-solvent to then make it into the dope that's going to spin a fiber. You then also have to bring the viscosity of that dope up to the right stage so you have filament stability in order to make sure you can make a good fiber. So it's not trivial, but we were able to do it, and this is a little bit of a snapshot of part of our system. We have a coagulation bath that we can change the length of to ensure we have good coagulation. These are some control fibers. These are some composite fibers as spun before any drawing or heat treatment. And this is a typical just basically cross-sectional shape. And these aren't great fibers. I show this cross-section because you want a round fiber. These are actually bean-shaped, which means that we haven't optimized coagulation and gelation yet. And I wanted to show that because we're still seeing the property bang, which is great. So if I look at the next slide here, what this is showing is a comparison of a controlled polyacrylonitrile fiber where we're starting to do this and a composite. And you can see an 80% increase, and the amount of nanomaterial is just coming from that paste. We're also increasing the amount of polymer here, and the reason we're doing that is we need to find the sweet spot to spin these. So we're looking at the non-Newtonian filament stability process. But what you can see here is as I increase the polymer, which means I'm decreasing the nanotube content, because I have the blended phase and I have such a good interaction, that actually extends out. The polymer keeps forming a larger and larger interface. So I'm actually getting better reinforcement of the fiber. So I'm using the nanomaterial in a way to help the polymer to self-reinforce itself. I'm not just trying to add more and more of it. I'm trying to make sure that the interaction really translates to the polymer matrix. So it's exciting for us because instead of just adding more, we're trying to really identify what is the sweet spot, what is the right volume fraction for a particular polymer system, and that's going to be very unique. So the last thing I just wanted to touch on, again, I'm just giving you a snapshot of the things that we're doing in our lab, but we're also doing this same type of, or this is the foundation. The dispersion is the foundation and it allows us to make a lot of different systems. We've been looking at carbonization, but also aerogel processing. So I'll touch on what we've been doing in carbonization, because for carbon fibers, that's why we use a lot of PAN. When you can create these types of interface structures around the nanomaterials, you can do it for a lot of different nanomaterials. So we look at few wall nanotubes, multi-wall, single wall, mixtures. We buy from everyone that makes it, the cheapest stuff to the most expensive stuff. And you can always make an interface structure because you can control the polymer, but will it stay stable under all of the processing conditions is a different story. And so here this just exemplifies that we can do it, and we can do it for a lot of different systems. But then when we try to carbonize it, and in this particular case we're carbonizing it only up to 1100 degrees C, which is not at industry standard, but it is something where we're forming a carbonaceous structure. What we found is that it really only survives, or you can form an amorphous carbon, but when you use single wall nanotubes, you can form a graphitic structure. Now why that's important is the single wall nanotubes have the smallest diameter, which means the polymer in that free volume, which is a small area, can get its arms around it a little bit better. You can form a more stable interface structure. But as you get a fatter and fatter nanotube, it's harder for it to form that structure, and that's really important in order to make sure to make the material stay dispersed. And again, these are not chemically functionalized. This is a physical interaction. But I show this because we were able to analyze the graphitic structures that we found with X-ray, and we can see that it's not the perfect hexagonal. There's some rhombohedral in there, but we are forming graphite. But what's really interesting is when I take those materials, one is, the bottom one here, is simply a film that I made that doesn't have any phase separation, and you see the carbonaceous structure, and this is the X-ray to prove that. But this is that two-layer film that I showed you earlier, where I know one side of the film has really nicely blended polymer phase with the nanomaterial, and the other side is those rejected nanotubes that are just kind of existing. So we kept track of those sides, treated it the same, and you can see very clearly here the graphitic layered structure. So at 1100 degrees, I'm forming almost a very perfect hexagonal layered X-ray structure. I'm getting that extra rhombohedral coming from this layer, and in a case where I don't control this phase separation, it's all intermingled, so you can kind of see that. So the point is that by getting this very, very nice interaction in this blended phase, it's not only having an effect on mechanical, but it's having an effect on processing of a carbonaceous structure. And if you could make graphite at 1100 degrees C, you can think about industry-wide how that would save a lot of heat in the processing. So we're working with carbon fiber producers to understand this more, because this could have a huge effect on processing. Right now you have to go upwards of 2000 degrees C to get a similar graphite structure. And then the last thing I'll show you is the aerogel work that we've been doing. So we're using this phase separation technique in order not only to help disperse nanomaterials, but also to help us to form polymer gels that have sort of these very small domain sizes, because it helps us when you're supercritical drying aerogels in order to make the structure, and helps the shrinkage. So this is one example where we're making aerogels that are sort of these three-dimensional puck-like structures, and we're trying to reduce shrinkage. But we're also making them in thin film structure, where we can make them opaque or we can make them clear, just depending on the processing. And we're trying to make something that is lightweight, but also thermally insulating, and sort of a better material than what we currently have, which is the silica aerogels that are very brittle. But the interesting thing is we're incorporating, in this particular case, boron nitride nanomaterials into these structures. And why we're doing that is one of the big things that we experience when you make an aerogel in the supercritical drying process is you get a lot of shrinkage and deformation. So what we're doing with these boron nitride nanomaterials is we're trying to reinforce the gel structure itself in order to make the gel structure a bit more mechanically robust so that it can go through the supercritical drying process and make a better aerogel using a very flexible polymer. And so these are the issues we have to get over. We also have to deal with bubbles and other things for transparency. But what happens is at the end of the day, these aerogels show some very unique kind of porosity structures, and we're getting some very uniform porosity in them, which is very exciting because the gels are very uniform, the structures are very uniform, and ultimately this is where we're at. We're able to make very thin film aerogels that have the Rayleigh scattering effect that you would see for a silica aerogel, and they're not deforming as much anymore. So we're successful in reinforcing these structures. We're successful in making them thin and getting this transparent structure. And all of that is coming from the learning that we have and how to disperse nanomaterials very nicely into a polymer matrix very specifically. So again, it takes a lot of tailoring for each system, but it's giving us insight into how to work with them a little bit better, meaning the nanomaterials. And then the last thing I'll just show you here is that this is just a comparison of the gels, the flexible one versus a silica. So you can see the silica is very brittle and this one is very flexible. So you have very similar structures, but you have one that you can use flexible. And we've done this over and over and over and over and over and over, and the polymer aerogel really is very robust. So we're excited about that. We're also getting nice thermal protection from them, so that's also exciting. And these are PVA, so they're not the best thermal polymer, but we're getting stability over hours and hours at 200 degrees C, which is pretty great. So it's an exciting time for us. Overall, the lab, like I said, it's focused on fibers and film, so dopes. Making those dopes are very important. Making them with high molecular weight polymers is very important because you need that for spinning. We're doing carbon fiber development. We're doing other types of fiber development, and we're coupling characterization with computation art to make that happen. So it gives you a snapshot of what we're doing, and I will end the talk there. Thank you.